Continuing with our study of derivatives, we're going to look at some more rules for derivatives. So far we've got the power rule, we've got the product rule, we've got the quotient rule, and always running in the background is the chain rule. Now we're going to look at trigonometric functions, their derivatives, and some higher order derivatives. And we'll explain that in a minute. So when we're talking about our trigonometric functions and their derivatives, we're talking about sine, cosine, tangent, secant, cosecant, cotangent. The two easiest to remember are the derivative of sine. So the derivative of sine is equal to cosine. Sine of x equal to cosine x. And the derivative of cosine is equal to negative sine of x. These are the easiest ones. So the derivative of sine is cosine. The derivative of cosine is negative sine. Now the others, not as easy to remember, but there is kind of a pattern to it, and I hope you see that here in a second. So if we continue on here, not ready for that. The derivative of tangent of x is equal to secant squared of x. So the derivative of tangent is secant squared, and the derivative of secant is equal to secant times tangent. Okay, now moving over to the other side, we said the derivative of cosine is equal to negative sine. Pause it for a second if you need to get all these written down. The derivative of cotangent is equal to negative cosecant squared, and the derivative of cosecant is equal to negative cosecant cotangent. And of course, all these functions are of some variable or of some value. So when I say secant tangent, I'm meaning secant x, tangent x. Okay, now take a look at these, see if you can see some patterns. Well, one pattern, I hope you notice, is that for all my derivatives on the right side, derivatives, all the ones that start with a cosine, cotangent, cosecant, their derivatives are all negative. The others over here are not. Derivative of sine is just cosine. The derivative of tangent is secant squared. The derivative of secant is secant tangent. Another pattern. If you take a look, I've got tangent here. Its derivative is secant squared. I've got cotangent. Its derivative is negative cosecant squared. So tangent and cotangent, they're related in that they're reciprocals of each other. Well, so are secant and cosecant. There's a similar relationship here. Secant and cosecant are not reciprocals, but they're reciprocals of cosine and sine, respectively. And there's a similar relationship here. Derivative of secant is secant times tangent. Derivative of cosecant, negative cosecant times cotangent. Okay, so if you take a look back over here, notice, again, derivative of sine is equal to cosine. That one's easy. Derivative of cosine is negative sine. That one's easy. It's these last four that kind of give people fits. But if you take a look, if you notice this one right here, I've got one tangent and I've got two secants. You just got to have them in the right place. Same thing here. I have a tangent and I have two secants. Over on this side, remember, if it's the derivative of a it's negative. I've got a cotangent and two cosecants. I've got a cotangent and two cosecants. So this is just one of those things you've got to memorize, but we'll be using it plenty, so hopefully you'll get it down real quick. Let's look at some examples. Let's say I want to find the derivative with respect to x of, how about sine of x minus cosine of x? Well, I can do that. I can find the derivative of each of these and subtract them. So the derivative of sine is going to be cosine x minus the derivative of cosine is the negative sine x. And so I'll end up with, well, that's going to be cosine x plus sine x. Simple enough. Now what we have to remember is all of our other rules that we've learned so far, all of our other techniques are still going to be in play. Let's try one like this perhaps. Let's find the derivative with respect to x of, how about sine, that's sine of x times cosine x. Okay, now what you got to recognize here, we've got a product. I'm taking sine times cosine. So to find this derivative, I've got to do the product rule, where sine of x is my first function, so to speak, and cosine is my second. So I've got to do my first, which is sine of x, times the derivative of the second. Well, the derivative of the second, the derivative of cosine, is negative sine x. And then plus the second part of my product rule, so sine of x times negative sine x there. It's hard to write with this deal here. So the first times the derivative of the second, and then I've got the second, which is cosine x, times the derivative of the first. The derivative of sine is cosine x. And so I can simplify this up. Sine x times negative sine x would be a negative sine squared x, or sine x quantity squared, plus cosine times cosine is going to be cosine squared of x. And this looks like one of our trig identities, but not quite. Remember, sine squared plus cosine squared is equal to 1, but our sine squared is negative here. Okay, also recall, so product rule is going to be in play, quotient rule, and especially the chain rule. Okay, remember, all of these trigonometric functions, well, they are functions after all. So if I have anything else other than just an x in any of these functions here, I've got to make sure to take the chain rule into account. What do I mean by that? Well, let's say y is equal to, how about tangent? Let's do tangent this time, of 4x. And I want to find the derivative of that. Okay, so my derivative, first derivative, y prime, well, notice what we've got going on here. I've got tangent as one function, and then I've got 4x is basically the other function, where tangent's my outer function and 4x is my inner. So I've got to take my derivative of the tangent, making sure that I'm going to chain rule my derivative of this with it. So how would that look? Well, so the derivative of tangent is secant squared. So the derivative of tangent x is secant squared x. So when I'm finding the derivative of this tangent, 4x, well, that derivative is going to be secant squared of 4x. But then I have to make sure and take it times the derivative of the inside. In this case, I'm looking at this as my inner function here, 4x. Well, I got to take it times the derivative of that, which would be 4. And this might just be simplified up a little bit by calling it just 4 times secant squared of 4x, with or without the parentheses there. So that chain rule stuff is always in play. That's what you got to remember. Now let's look at some other type of examples. Must be very careful when we have different powers of trig functions, because where the exponent goes is very important. For example, we've said in the past, if I have perhaps a function like this, f of x is equal to, I don't know, how about secant squared? Let's just say secant squared of x. Okay, remember what this means. This is the same as secant of x times itself. Okay, so if I write it out this way, that's what I would recommend. Whenever we're looking at a trig function to a certain power, rewrite it like this. Because then hopefully you can see we've got, again, a function here, secant x, inside of another function, squared. So now if I want to find the derivative of this, well, I'm going to have to use my power rule here, so I'm going to bring down the 2. Leave this alone in here and subtract 1. So that's going to be 2 times secant x to the 1 power technically. And then I have to take it times the power of the derivative of the inside. Chain rule. Derivative of the outside, leave the inside alone, times the derivative of the outside. Well, times the derivative of secant. The derivative of secant is secant x tangent x. And then I could simplify this up a little bit by combining, just multiplying all this together. So I'd have 2, and I have 2 of the secants, secant squared, and then times the tangent. Tangent x there. Okay, now that's different than, let's say I had a different function that was secant of x squared. Okay, it's a very subtle difference, but notice here my squared is on the secant. I'm squaring the secant. Here only the x is being squared. So in this case, the secant is my outer function, x squared is my inner function. Back up here, secant is the inner function, and the squared is the outer function. Very small difference there, but when I take the derivative, it makes a big difference. So if I take the derivative of this, it's going to be the derivative of the outer, which is secant, and the derivative of secant is secant tangent, but not x this time. It's going to be of x squared. So the derivative of secant x squared is going to be secant x squared times tangent x squared, and then I take it times the derivative of the inside. Well, again, x squared is my inside function here. This is my inner function. So take the derivative of x squared, it's going to give us 2x. And to complicate things perhaps even further, let's look at something like this. Let's look at y equals, let's call this one cosine cubed of, say, 3. No, let's call it 5x. Cosine cubed of 5x. Okay, now remember, sometimes it's better if we rewrite this. So let's write this as the cosine of 5x, quantity cubed. And let's find this derivative. Well, if you'll notice what we've got going on here, we've got our outermost function is this cubed. Within that I have a cosine, and within that I have a 5x. So this is technically a function inside of a function inside of a function. And this is why we call it the chain rule, because I got to keep going. All these pieces are chained together. I got to keep taking it times the derivative. So let me walk you through this, how this might look. This derivative here. Again, start at the outermost part. I've got the outermost function I have is something cubed. So just ignore what's inside of here. This is just something to the third power. When I take the derivative of something to the third power, I'm going to bring down that third power. That's something, and then it's going to be reduced by a power of 1. There's my power rule. So this is whatever's in there. I leave it alone. So I can plug it back in there. So instead of 3, if this was x cubed, I'd have 3x squared. But it's not x cubed, it's cosine 5x cubed. So it's 3 times cosine 5x squared. Okay, so there's the first part. Now I've got to take it times the derivative of the inside. Well, in this case, the derivative of our inside is cosine 5x. The derivative of cosine is negative sine. So the derivative of cosine 5x would be a negative sine 5x. Leaving the 5x alone, because now cosine is my outer part, or the middle part. Inside of it is the 5x, and so now I got to take it times the derivative of the innermost part, which is 5x. So times that derivative is just going to be times 5. There's a lot going on there. Okay, I've got 3 different functions. If we looked at each of these, my outermost function is x cubed. If I broke it down, within that I have a cosine function, and then within that I have a 5x. And this 5x becomes, this 5x goes in here, and then this whole thing goes in here as I decompose it. So here's my derivative. I can clean this up a little bit. I got the 3 and the 5 I can multiply together. I have a negative here, so this might look like negative 15 cosine squared of 5x times sine of 5x. When we're talking about higher order derivatives, we're basically talking about derivatives of derivatives, also known as second derivatives. And then we can take the derivative of that and get a third derivative, fourth derivative, fifth derivative. We can go as far as we want. Okay, now the notation, as you might expect, our first derivative is y prime, or f prime of x, or maybe dy dx. Okay, these are all our first derivative. Second derivative, I'm going to abbreviate. Our second derivative, well, is going to be like y double prime is our second derivative, or f double prime of x. And our other notation looks like this. It's the second derivative with respect to y of x, like that. Now, why do I have the exponent on the d here and on the top and the x on the bottom? Well, basically what's going on here, I've got dy dx as my first derivative, and I'm going to take the derivative of that. I'm going to take the derivative with respect to x of that. So if you look at this, it's not really what's going on, but think about this algebraically. In my numerator, I've got a d and a dy. Well, that's 2 d's and a y. So that's like d squared y. We don't say d squared y, This is called the second derivative. But in my denominator, I've got a dx and another dx, which is almost like saying dx squared. If I had a third derivative, I'd use y triple prime, or maybe even this. And why do higher order derivatives matter? Well, this is where physics comes into the equation. If you've had physics, you maybe have done some calculus type stuff, but not likely. From here on out, if you take a physics class, most likely it's going to involve some calculus. Okay, so we're talking about functions in relation to time. And we have three of them, three different functions. We've got our position function, we've got our velocity function, and we have our acceleration function. Okay, position, well, most often we've got, okay, for our textbook calls our position function s of t. S of t is the distance as a function of time. Okay, it's the distance something's moving. Now, that change in distance with respect to time, well, the change in distance as the time is changing, this is like our slope and the velocity. Okay, as distance changes with respect to time, that is our s prime. It's the velocity, it's how fast something's moving. It's the speed, if you will, even though velocity has a sign associated with it. Speed can never be negative. Velocity can, because it tells us direction. Okay, so our change in distance with respect to time, as time changes, our rate of change is the velocity. And as the velocity changes, as our velocity changes with respect to time, our rate of change of velocity is our acceleration. So velocity is the first derivative of position. Acceleration is the first derivative of velocity, which makes it the second derivative of position. Lots of practical applications here when we're dealing with this stuff. For example, let's say I were to drop a ball from a height of 50 feet. Okay, where S measures the position and T is the height. The position, I'm sorry, T is time. S is the height of the ball, its position. And in feet. T is in seconds. So our function might look like something like this. S of t equals negative 16t squared plus 50. 50 is our initial height. It's our initial position. And we'll deal with lots of these types of problems later. But if I want to find the velocity, let's say I'm asking for the velocity after 2 seconds. Okay. Well, if I want to know the velocity, I'm looking for the rate of change at the position, which is going to be the first derivative. Okay, so I'll take the derivative of this. Well, derivative of minus 16t squared, I'm going to bring down the 2, multiply it times the negative 16, so that'll be a negative 32. Subtract 1 from the exponent, t, plus 50, or the derivative of 50 is going to be 0. Okay, so my velocity then, when t is 2 seconds, I would just plug that in. So this is going to be negative 32 times 2, negative 64. And since again, this is like our slope. Okay. If our position is measured in feet, we said from 50 feet. So feet would be on our numerator, and t is our time in our denominator, or seconds. So it's dropping at a rate of negative 64 feet per second. Negative telling us it's going down towards the Earth. And if I want to know the acceleration at that same time, well, the acceleration with respect to time is the derivative of velocity. Well, I already had the velocity as negative 32t. Okay, so the first derivative of that, of negative 32t, is going to be negative 32. And if I plug in 2, the velocity, well, I don't have anything to plug in there, so it's just going to be negative 32. And this is going to be the change in velocity over time. So this is going to be feet per second, or feet per second squared. Okay, so here's your assignment. We're going to do some of these in class for sure. See what you can get done this weekend, and we'll talk about it on Monday. And oh yeah, it'll be Monday, so MC Monday, yay!